Hello and thank you for joining us at the virtual Malvern Festival Innovation here in the studio. I'm joined by Nick Tudor, who's the CEO of De-Risk Limited, a company based over in the Malvern Hills, and we're going to talk about both his company and the software tools that he's developing. So Nick, welcome. Thank you for joining us.
Thank you, Adrian.
So you've been on quite a long journey since I think 2012 or so with your company De-Risk. You're a software solutions company developing tools. Could you just give a little bit of an overview about what these tools do and why they're important?
Yeah, sure. So software has to do what you want it to do, and crucially not do the things that you don't want it to do ever. And unfortunately, being able to do that is kind of difficult. You have to be able to show evidence that it's safe or show that it's secure, and particularly in regulated environments. Otherwise, it's going to cost you an awful lot of money and time to do the things that you want to be able to do without the software. And even if you do things well, it's still an expensive process. And particularly thinking about aerospace, where people have never died as a result of software using the standards that are available out there. So adopting those kind of processes is seen to be slow and expensive. It's not if you're good at it, but you really do have to know what you're doing. So what we've developed is a series of tools that actually puts the maths into software engineering. So engineering is the application of mathematics and physics is the application of mathematics. So it's maths all the way down if you're doing engineering. So most people don't know that there is a mathematics for software. There is. It's called formal methods. And what that enables us to do is to do proof. And because it's proof, formal methods means subject to mechanical analysis. Because it's proof, then you can actually avoid the need to do things like subjective reviews, because you've got objective evidence that an artifact satisfies what it's supposed to do. And proof then can be automated. So by doing that, what you're doing is speeding up the development process. And therefore it's important from an economics perspective, from both the company and from the UK's perspective, to be able to do these things faster and cheaper, but very, very assuredly.
So I mean, software is in lots of things. You mentioned some of the critical areas. So I know you work with aerospace, automotive, nuclear decommissioning type applications, cybersecurity. I mean, those are key areas where there are safety issues. So if somebody's working on those nowadays, developing some software, what sort of things do they have to think about and go through in order for it to work at the end then?
Right, so there are standards that are available out there. They are written generally by industry with a regulator sort of insight into them. Sometimes they're written by the regulator, and that tends to be a pretty bad thing to do. But what you end up with is broadly all of the standards that are out there are in essence the same. And that is, you have to have a set of system requirements or customer requirements. If you're a software engineer, your customer is your systems engineer. And those have to be clear, unambiguous and stable, and typically they're not. There's a review process that goes on, but then that gets transformed into some software specification, if you like. Right. And that's in a language then that a software engineer can use to do a number of things. Firstly, to do a development, but also be able to communicate to the person who's doing testing or the verification that this is what the behaviour is supposed to be. Yep. And the third sort of set of stakeholders, really, on behalf of the general public, is a regulator. So you describe what the software is supposed to do. So then you go into the design phase, and then you have to show that design phase has correctly, completely, accurately captured all the specification. You've not introduced stuff that wasn't asked for. You've not missed out anything, and it's all correct with respect to the requirements in the specification. And then you have to go into a coding process, and you do the same set of processes again to show that it's complete, correct, etc. And then we throw it over to a machine called a compiler, and that turns those if-then-else statements from the source code into the binary or the executable object code that goes onto the actual processor. And then you have to show that image on that processor actually does satisfy the requirements in the first place. So it's like any other engineering process. If you want to build a bridge, you don't just start digging holes and pouring concrete and then say, by the way, where do you want the bridge and how much traffic do you want it to do? You don't start coding and then say, what does the customer want? There is supposed to be a process behind that. And unfortunately, an awful lot of people think that software engineering is all about the code, and it's not.
Yeah. I think a lot of people probably think that with software you literally do just start writing it and that's fine, because people do that in their back bedroom. But
Yes.
when it's critical systems, you've still got to go through the design process, as you've explained. So you gave some sort of abstract examples. Have you got some specific case studies where that would work, like with autonomous vehicles or things that you've worked on?
Yeah, so we're in the middle of 2 programs. One is a project for a medical device, and it's critical, shockingly enough. The software has to work. It's for organ transplant or transplant organ transportation, and you need to know that the science that's keeping the organ viable actually has done what it's supposed to have done over the very long extended periods now that we're talking about, over 3 times what you can do at the moment, which is amazing sort of bit of science. But the control over the environment in which that transplant organ sits and the reporting of what's actually happened is therefore crucial to the clinician, who ultimately has to make a decision whether or not to use that organ for transplant. So yeah, we're having to do that, and we're starting on the regulatory path there this year with the Food and Drug Administration in the US as a minimum. And the other one is an unmanned air vehicle where we've worked in autonomous vehicles in all sorts of sectors: air, land, subsea, on sea surface as well. And there's plenty more of that coming. But the functionality in an autonomous vehicle largely rests in software. So it only has to be more than 51% for that to be right as a statement. So what we're saying when we don't trust an autonomous vehicle is we're saying we largely don't trust the software. So what we've proposed is actually written in standards already, is that we have an independent, high-integrity safety monitor that assesses what's going on in the environment and can therefore make decisions. Like any software, it relies upon the data that's given to it and an architecture that sits around it. So it's not just the software, so the safety aspects are largely, but not solely, in software. And our software development process with our assurance complies with the software standard for civil aerospace. So in fact, the formal method supplement to that standard.
Okay, and I mean, we're hearing a lot about artificial intelligence, machine learning, and that's being used in software to help autonomous vehicles and things. Where does what you're doing fit with how AI may come in the future?
So AI is a bet. So all AI cannot be assured. People say it's not deterministic. Actually, at the binary level, it is. It's just a program. It's ones and zeros at the bottom. But what we're basically saying is we can't model the environment adequately. And what we're going to do is we're just going to guess. We're going to learn how much this bit of software we've done actually can react to the environment in which we've got to put it in. So because it's a bet, there was a brilliant presentation done last year which really showed this. I won't name names, but it was an academic from the UK who said we've gone from thousands of data samples through tens of, hundreds of, millions, tens of millions, and now into many billions of data items that are being used to train this particular piece of AI. And he said, as a result of that last step to the many billions, we've gone from 94.8% confidence to 95% confident. So what we're doing, in summary, this is my summary of that, is that we're going exponentially increasing the data pool for training, and we're asymptotically not achieving where we need it to be, which is 99.99999% confident. So what we do is say, right, well, that has a place. There's no doubt AI has a place in all sorts of different industries and the way in which it's being used in different sectors. But there has to be an independence in some way, shape or form that sits alongside it that can be assured. So what we've done is effectively defined a safety cage using our tools so anybody can understand what the behaviour is going to be and the limits of the behaviour. So the AI can bounce around inside the cage, giving all the performance stuff that people want or might need, up to the limit. And the limit just cuts in. That's the easy bit, is just cutting in. The question is, what are you going to do instead of? So if you're offline and you're doing some assessment of some imaging, for example, of breast cancer or whatever it happens to be, then there's no imperative to actually do anything as such right there and then. You can take a few minutes, hours, days to make a decision. But if you're on a vehicle, if you're in the air and it's unsafe, you've got to make a decision about, now, what are you going to do? And that's the hard part, and that's the bit that we've tackled.
So in that case, you would use AI as an opportunity, and then you're tools that help address that ring fencing, those safety guards, you're basically making sure that the software that takes over and deals with the situation deals with it in a prescriptive, safe way.
Yes.
Yeah. Okay.
And then when it's safe, you can hand it back to the AI and go, carry on, until it
does it again. Yeah. Okay.
Yeah.
So you've talked about your tools generically, but do you want to say a few words about what they are, what they're called? Because I know you've got a suite that you've been developing.
Oh, it's very sweet, yes.
Yes, sweet.
So we have a tool called System Capture, which enables systems engineers to write clear, concise, unambiguous requirements. There's a notion of completeness that goes on with that. And for example, we just did a study in the nuclear for the nuclear industry in the UK, where we modelled a steam boiler. We know what that is, of course, a kettle, if you like, a rather complex one. And one of the things we want to explore at the requirements level. If we want this thing to turn off, and there are times when you do want it to absolutely turn off, will it always turn off? And the key word there is always. And we explored our specification at the time, right at that sort of system requirements level, and we showed there was a very small corner case where it wouldn't turn off.
Right.
So now you can fix that at the beginning of the process. So you haven't spent any money doing design, code, haven't built anything, but you now found out an issue that would have gone all the way through the process potentially.
So is that specification written in English?
It's written in English, yeah.
Okay.
So we get interns at 16 years old, no qualifications whatsoever, using these tools. So it is very simple. So a typical software developer can use these tools, and we've got people using them in industry now. So that's system capture. Then that gets elaborated. So there's more detail for a software engineer to give the software requirements out there, the software specification, and that's called capture. And then we show that specification specifies the system requirements, and then those two tools together. And then a design's done in a typical control language called Simulink and Stateflow. So that's what most people use out in the automotive, aerospace sectors, etc. But how do you know this? It's like a circuit diagram, if you like, a bubble and line diagram. So how do you know the bubble and lines satisfies the English? Well, we translate all of that to a mathematical representation under the hood, so you don't get to see any of that. You don't need to know how that works at all, it just does. And then we can prove using ModelWorks, our tool, that the design in Simulink Stateflow satisfies the requirements automatically. And as a byproduct, on all these tools, you get the evidence to satisfy the certification, the regulator. Then we use an autocoder, and that's off-the-shelf autocoder from DSpace in Germany. Their Target Link autocoder produces a program in C, and then we independently check again, translate to the maths, and show that the program now satisfies the design. And then that's Clause doing that. And then this year we'll have a tool called Fever, which again independently shows that the compiler hasn't made any mistakes as well.
Okay. So there are multiple levels then. You've got to look at each of those sort of separately. And you mentioned C. So is it only apply to C, your tools at the moment? And what about other languages in the future? Yeah,
so one of my co-directors, Colin O'Halloran, he was the technical authority for what was called the Spark subset of the Ada programming language, and that was back in the 1980s. He's not going to thank me for that. So that was the first commercially viable subset, if you like, of a programming language with formal semantics behind it to enable this proof to be done. And then when I joined him in the early noughties, I suggested a program where we formalised the subset, did a formalisation of other programming languages, including C and C++.
Yeah.
So we did that, and we know the process of doing that and how to do that for as many languages as we like now. So the focus is on embedded real-time. C gives us what we need in that regard. Other languages have lots of unsafe behaviours behind them, undefined behaviours. So we do have a subset of C++, but it's largely what C looks like because it's very closely aligned languages.
And it's used widely in the industries that you're using. Yeah, makes sense. So, so you have a team in the Malvern Hills Science Park where you're based, working on these tools. How difficult has that been to bring these to market, to test them, to get collaborators and potential customers on board?
That's been an entertaining a few years, that's for sure. The team are fabulous, don't get me wrong, but what we've had to do is to trial out what works with various potential clients. So we've been fortunate, if you like, we tried very hard and managed to get a number of programs through Innovate UK and other commercial programs where we've had potential partners, future partners working with us saying what's good and what's bad, what's the scope of these tools. So that's in automotive, in aerospace, in various sectors, autonomous systems and what have you. So that's the approach we've taken. So we've trialled the tools, get the feedback, so we know that's what needs to be fixed, and then that goes out and we find some more issues. But what we're not doing, we like a lot of entrepreneurs, we kind of fell into the trap of trying to chase every little tiny thing. And that's one person's whim as opposed to others, so we stopped that pretty quickly. And then went on and said, right, this is the core minimum viable product that should apply to an 80-90% approximation of the entire market. And of course, it's at our whim that we can add extra stuff should we need to, and that is the plan, obviously, to expand the capability, including other programming languages.
So, I mean, along that journey, you've been on some accelerator programs and some overseas trips, for example. I think
yes,
with
don't tell my
UK.
wife.
Yeah. So, so which ones of those have been useful to you then, and what do you get from being on one of those programs?
So all of those programs have been useful. So sometimes they prove a negative. So there's one program I went on to the States, to San Diego, and I think all of us went to a 90% approximation and said that just showed a negative. So that's valuable. It's good to know that don't waste your time going there. So like any research, showing a negative is good outcome. So in terms of positive, again, we've been on the global business innovation programs and global incubation program into Nova Scotia in Canada. Focused on our autonomous systems. Now, we also got a small grant program out of that as well, which gives us relationships into that region, and we're still following up on those. Those are long-term relationships that we need to have, knowing our sector is embedded real-time systems, which nobody else really recognises out there, because either you're in the automotive sector or you're in the space sector or in the whatever medical devices sector. So we're in the embedded real-time systems sector, which can go into all of those. So it's quite difficult for us to actually get, like somebody who's focused on aquaculture, going specifically to a place that wants to do aquaculture, and that's 100% match. So they're going to get much better value out of this. We launch into things where we want to get into. So, for example, we were on the inaugural Airbus Space and Defence Space Accelerator at the back end of last year. And has to be said, the selection process whittled down from many hundreds, I understand, many hundreds, down to about 30 or so that were interviewed. And we were one of the 9 that were taken through. So a company like Airbus is seeing something in what we're doing. We haven't got space written across our forehead, but it's obviously something that applies into space. And that's why we're on the accelerator. So that kind of program is what we look for, and getting exposure and getting the marketing collateral as a result of being on those things. Yeah,
because yours is really a platform technology, so it can apply to so many different sectors. I mean, you mentioned medical at the beginning and obviously aerospace. I mean, I guess that's one of your big challenges, is knowing which ones to focus your energy on, because you're a small company and you don't know all the nuances of these different sectors. So at the moment, what's your focus?
So you're right. The nuances, we now know most of them.
Right.
We've been there and touched it and found out. And as I say, at the root of this, it's just software engineering. Software doesn't care whether it's underwater or in space or anywhere in between. So the focus at the moment is for us to support the medical device and the unmanned air vehicle, and that's these 3 months now are crucial to that, or 2 months, in fact, 6 weeks for the unmanned air vehicle. So those have to be out and demonstrated, and the prototypes shown out in the US for the medical device than in the UK for the unmanned air vehicle. But in the background, there's quite a lot of other things going on. So there's some cybersecurity work that's going on as well, which we won't talk about that specifically today. But that's not using our tools, but it could lead to something for us in the cybersecurity market in due course. And the whole thing about digital security by design is now out there, and in fact that's where I'm off to after I finish this interview for an event down in London. And more pertinently perhaps, there is an initiative that's just come from the Ministry of Justice, which launched on the 21st of January. If you use your favourite search engine of choice, Ministry of Justice and computer software, use those words in the search, you will find that they're calling for evidence as a result of the law currently, as established in the year 2000, was that computer evidence is taken as fact, regardless. Right. Now they're looking to see whether that law should be changed, and there is a fabulous set of half a dozen or so questions, which basically, if what those questions allude to, A, the law will change to that presumption of innocence, if you like, on the software. 2, you have to show that the software does what you say it does. And crucially, particularly in the case of Horizon, as you may have seen the material on that, you have to show that it doesn't do what you don't want it to do ever. That's a sea change potentially a sea change in British law, and from our perspective, that is exactly the hymn sheet that we've been singing to for over 12 years now. So
that's another kind of unexpected opportunity in that.
Yes,
it's another area that's evolving that you can step into. So going forward then for de-risk, I know you've had some investment already. What's the plan to grow the company? Are you looking for more investment? Are you looking for a big customer partner? How do you see it growing over the next 2 to 3 years?
All of the above, really.
Okay.
So we're looking now to scale. The tools are the first. So the first 3 tools, as in Capture, ModelWorks, and Claws, are ready. System Capture we're keeping to ourselves for the time being. There's some tinkering that we need to do with that to get that so that it's easy for customers to use. And Fever coming out later this year. So we're looking for that license approach. We've been talking to a lot of small companies, a lot of large companies, talking to government organisations as well in the UK, and obviously partners overseas. We're doing a programme in Germany at the moment to extend some of our capability as well. And obviously doing projects so we can show what the art of the possible is, and we can get the finance officers in companies to say, hang on a minute, how come they're doing it for 20% of the cost that you can do it? Why is that the case? And we can show why that is the case. Productivity is off the scale compared to traditional approaches, that's for sure.
And I think that's probably the key that we didn't really elaborate on, is that the whole point of what you do is not just the safety, but it's actually lowering the cost of the whole development along the way.
Yeah, so I mentioned the study we did for the nuclear industry. It depends where you benchmark, and there are no good metrics for how you cost software as far as I can tell. I was at a conference last week where everybody agreed that was the case so far. But it's typically measured by lines of code, and the project manager wants lines of code, functionality. Well, I've just described that we can do at the systems level, we can get the functionality much better than than is possible currently. And that process, using all our tools, we managed to produce 5,500 lines of code in 6 labour weeks, which works out at being about 186 lines of code per day. Which the best I've ever heard of is 38 lines of code per day. So we're 5 times better, 4 or 5 times better than I've ever come across. That was world class. There was 2 academics using their own tools to do a very tightly controlled project. So most people, by definition, are not world class. And there's some facts on our website that talk about the range that this could be. Lines of code is not the right measure per se, but there isn't a better one. The focus is on getting the requirements and the design right, which is your intellectual property. It's not in the code.
Very good. Well, Nick, thank you very much for joining us. It's great to hear the background and also some of the future possibilities of what you're doing. Good luck, and I hope your trip to London later goes well as well.
Thank you very much.